Okay, so where we left off last time, we were working with Riemann sums, and the idea is we're trying to estimate the area under the curve by putting rectangles on it. And we want to remember that we had three basic ways we were choosing the points for these rectangles, and we're going to use one of these for this example problem in a second. But the three basic ways that we were doing this is we were using left endpoints, we're using right endpoints, we're using midpoints. In reality, it doesn't matter what point you choose unless you're interested about how fast it's converging. But we're going to apply the technique to an example problem. And let me just pull that up over here. Let me laptop. Okay. So the example problem is reading the velocity of a car in feet per second is recorded from a speedometer every 10 seconds, beginning 5 seconds after the car starts to move. All right, see table 2. Use a Riemann sum to estimate the distance the car travels during the first 60 seconds. All right, each velocity is given at the middle of a 10-second interval. The interval extends from 0 to 10 and so on. Okay, so we have time and we have velocity, and we're going to see this again. If we want to look at distance, does anyone have an idea of why we'd be looking for the area under a curve here? Any guesses? Well, yeah, we can get a distance equation. That's true. We know that from the last section. But just in terms, not in thinking in terms of the antiderivative, which this is ultimately related to, we'll see in the next section. But just in terms of finding the areas, does anyone have any idea? It asks the question, where was it? Use Riemann sums to estimate the distance the car travels during the first 60 seconds, right? But all we're doing is drawing rectangles, right? All we're doing is drawing rectangles here, and all we have are velocities and times, right? So how does this relate to the distance? Okay, so let's maybe take a look at that before we start the problem here. So let me just flip over here. Can everyone see that okay? It's coming in a little dark. Okay. So suppose we had a constant function before we go to this, before we go and do this problem over here, suppose we had a constant function was as v of t is equal to 5 miles per hour. Okay, can everyone read that okay? Suppose we had a constant function here. So the velocity is we're going 5 miles every hour. All right? Can you see it better now? Here, let me write a little thicker. Suppose we have v of t is equal to 5 miles per hour. Is that better? Yeah. Okay, good. All right, so if we look at this function, this is a constant function, and let's just look at it over the interval, say z is less than or equal to 5 hours, and t is greater than or equal to 0 hours. So let's just look at it over there. And so if we draw this out, we're basically going to have, here's 0, here's 1, 2, 3, 4, 5, right? And we have a constant function. Now, I chose these 5s the same just by coincidence. There's no relation there. I just was writing and a 5 happened to appear on the paper. All right? So, v of t is a constant function. So, v of t here is equal to 5. Say this is the point 5 over here. Right? Now, if we graph this function from 0 to 5, okay? And we find the area under this curve. The area of this curve is going to be a rectangle. What's the height of this rectangle? 5, right? And what's the base of this rectangle? 5. So what's the area of this shaded region in here? Right? It's going to be 25 25 what? What is it going to be? Well, velocity is given over here, and we just multiplied it by the time. So did everyone agree that the area in this box is going to be 25? Right. What are the units of this area? What is it? Well, what are the units of velocity? So the area in here, the area, I'll just put A for area, is equal to 5 miles per hour, right? Times what? What's the base of the rectangle? Well, 5 hours, not 5 seconds. So we're multiplying by 5 hours, right? So if we cancel the hours, what do we wind up with? 5 what? Well, not 5. We have 5 miles per hour times 5 hours is going to be 5 squared miles, which is what? 25 miles, right? Okay. So basically, by finding the area in this curve, we found the amount that we've displaced after 5 hours. All right. So it's easy to see that when we have one rectangle, and we're going to deal more with that in the next section. But if we go back to the problem in the chapter, that's kind of what it's getting at here. So if we go back to this problem, it says use a Riemann sum to estimate the distance the car travels during the first 60 seconds. Okay, so finding the area under the curve is going to give us an idea of how far this car displaced after the first 60 seconds. So basically, if we want to know how far this car went, we can estimate the area under this curve. Now we're starting from 0, and our intervals are going to be of length 10. So we're going to use this chart over here where you're going to see the time is going to be our midpoint, and the velocity here is going to be how fast the car is going at that time 5, 15, 25, and so forth. Okay, so let's take a look at that. Okay. So we had our table here. And the table was given by, we had times, and we had velocities. Okay? And the first time we had was 5 and 20. Then we had 15 and 44. Then we had 25 and 32. Then we had 35 and 39. Then we had 45 and 65. And then we had 55 and 80. Okay? Now, what we're going to do here is, just to get an idea of what's going on, we're going to just do this on a number line. So the initial time, we're spacing them by 10, so it's 0. Then we have 10. Then we have 20. Then we have 30. Then we have 40. Then we have 50. And then finally, we have 60. Okay, so if you'll notice what they did is they gave us the midpoints on this interval. Can everyone see that all right? Anyone not see it? Okay, so what we're going to do here is 5 is going to be our first midpoint. And at 5, we had a height of 20. So I'm going up to 55, so I'll just go 10, 20, 30, 40, 50. And so these are by tens. Now the first one has a height of 20, so it's going to be this rectangle up here, right? Now the second rectangle has midpoints, is going to be 15. And at 15 the height is what? What's the height of 15? 44. So what's going to be the height of the rectangle? 44, right? So this over here is going to be 44, so it's 10, 20, 30, 40 is going to be up here. And we're going to draw this rectangle. Notice the heights are corresponding to the midpoints. And we're going to go again, our next point is 25. And notice 25 is the midpoint between 20 and 30. So I'm going to have my 25 right here. And the height of the function at 25 is going to be 32. So it's going to be slightly above over here. Right? And I just keep doing this. So this is going to be 35. And for 35, it's going to be about 40. So it's going to be 10, 20, 30, 40. It's going to be about slightly less than this one. And for the next point, which is 45, for the next one, which is 45, this is going to have height 65. So this is going to be about right here. And then my last midpoint is going to be the midpoint of 50 and 60, which is what? 55. And what's the value of my function at 55? 80. So did I make enough? Oh, no I didn't. Okay, so it's about right here. Okay. Okay. So what's the base of each of these rectangles? 10. And the height of the rectangles are these values right here. So what basically we're going to do is we have how many rectangles here? 6. So the area is the amount the car displaces is going to be the area under all these rectangles. And the area of all these rectangles, we're just going to find the area of each rectangle. The base of each one is 10. And we know that the height of each rectangle is just going to be, the first one is going to have height 20, 44, 32, 39, 65, and 80, right? So if we just find the area of these rectangles, I'm just going to use A to represent area. But before I do this, any questions on what I've done so far? No questions? Okay. So I'm just going to let A be my area. And the area of my first rectangle is going to be 10. And what's the height of my first rectangle? 20, right? It's going to be my first one right here. So it's going to be 10 times 20 plus 10. What's the height of my next rectangle? 44, good. And then we're going to have the height of the base of my next rectangle is 10 again. And the height of my next rectangle is going to be 32. And the base of my next rectangle is going to be 10 again. And the height is going to be 39. And is going to be 39. And the base of my next rectangle is going to be 10. The height is going to be 65. And the base of my next rectangle is going to be 10. And the height of my next rectangle is going to be what? 80, right? So if I have this right over here, notice that the way we're doing it in this section, now in reality you don't have to have all the rectangles have the same base. You don't even have to use rectangles. All right? But these all have a base of 10. So we can factor this out, and this is just going to be 10 times 20 plus 44 plus 32 plus 39 plus 65 plus 80, right? And if we sum all these up, we're going to get 10 times 280, which is equal to 2,800. Okay, so let's go back to the problem in the on the slide, and let's go through how they do it. Let's see here. Okay. Okay, before I do that, it's 2,800. What are going to be the units of my answer before we go on? What should be the units of my answer? What? Well, in the example I did on paper, it would be miles, but in this example right here, what would be the units? 2,800 what? Feet, right? Because what that example I did was to kind of illustrate the fact we're estimating the amount the car is displacing, okay? By estimating the area under the curve. So it's going to be 2,800, but just to see kind of how they approach it, the spacing is 10, we know that. So they estimated what the curve might look like, and they put the triangles beneath, the rectangles beneath it, and essentially the same thing we did over here. Okay. Any questions on this? No? All right. Okay, so the next thing we're moving on to is we're going to look at something called definite integrals, and we're going to look at something called the fundamental theorem of calculus. And basically, for the definite integrals, we're going to be looking at the area under curves again, and we're going to kind of extend that to get a relationship to the derivative. All right? So, and the reason you're going to, we don't really talk about it much, but the reason we're sticking to continuous functions is so we can think, yes? What? The test is going to go, well, I'll answer any questions about the test after class. How about that? Okay? So, okay, so, and as we're going to say, the reason we're going to want them to be continuous, we don't really deal with it in this class, is so we can look at the derivative in the integral as inverse operations, right? So we want to restrict our attention to continuous functions. So we're going to look at the definite integral, and you're going to see how it's related to the indefinite integral, as going to be a bunch of rectangles. And the idea is if we use more and more rectangles and we make the rectangles smaller and smaller and smaller, then eventually we should know what the area under the curve is, right? So that's what this definition is saying here. And I'm just going to illustrate that real quick. So to illustrate that idea, but let me just pop the definition up there again before I illustrate it. So does everyone recognize, if you ignore the Riemann sum, does everyone recognize that, if you ignore the limit sign, does everyone in here recognize that this is just a bunch of rectangles being added together? This is the height of the first rectangle. This is the base of the first rectangle. This is the height of the second rectangle. This is the base of the second rectangle. And so on. This is the height of the nth, whatever n is, the 100th, the 50, whatever it happens to be. Say n is 50. This would be the height of the 50th rectangle. This would be the base of the 50th rectangle. So does everyone understand? If we ignore the limit sign here, we just have a bunch of rectangles being added together. Is everyone okay with that? So the idea here is, and we're going to see in a second, we're going to use this relation. We're going to if we let the rectangles get more and more and more and have smaller and smaller bases, eventually we wind up with the area under the curve. Okay. So just to illustrate that idea, we're going to do an example in a second, but just a quick illustration of what it is. If we have, I don't know, a function that looks like this, and we wanted to estimate the area under it, we might find a partition as follows, and we might look at this first rectangle, and then we might look at this second rectangle, right? And then we might look at this third rectangle, and then we might look at this fourth rectangle. All right? Now, suppose we made our rectangles smaller. We're going to have more rectangles. But if we were to make them smaller, the idea is we get a better estimate of the area. And if we make them, if we even add more rectangles, and if we make more rectangles, they're going to have smaller bases. We get a better and better estimate of the area. And eventually, and that's why we're taking a limit as the base of the rectangle goes to 0. If we just keep doing that and doing it over and over and over again, the idea is that eventually we wind up with the area under the curve. So if we do that again, and I'm going to draw the same curve, except now I'm going to make more rectangles. So the first rectangle is going to be something like this now. And the second rectangle is going to be something like this. Sorry. And the third rectangle is going to be something like this. And the next rectangle, say, is going to be something like this. And the next rectangle here is going to be something like this. Now, can everyone see that this is going to be a lot closer to the area under the curve than this one over here? And if I make more partitions and I make more rectangles, I'm going to get a closer answer. If I keep doing it, I'm getting closer and closer and closer to the correct answer. Does everyone get a gist of what's going on here? So essentially what we're doing is we're going to use this to find areas under curves, okay? All right. Okay. And that's why we have this limiting process over here, is because as the base of each rectangle goes to 0, we're sticking more and more rectangles under the curve. So we're letting the number of rectangles go to infinity, and we're summing up more and more rectangles that are smaller, and they're fitting better under the curves, and eventually we wind up with the area under that curve. All right. Okay, so the first problem that we're going to do here is, since we're going to define, what we're going to do here is we're going to calculate the area under this curve from 0 to 1 of x plus 0.5 dx. Okay? So the basic way we're going to do that is we're going to start out by graphing it. Okay, so we have the integral from 0 to 1, and we're defining this as a definite integral of x plus 0.5 dx. Okay, so essentially what we want to do is we want to find the area between we want to find the area between this curve and the x-axis, between the x values of 0 and 1. So in the definite integral, these two values here are going to be your bounds on the x-axis. All right? So let's start out by graphing it. I'm going to let y equal x plus 0.5. All right? Okay. So first of all, what kind of curve is x plus 0.5? Is it a parabola? Is it a hyperbola? Is it a constant? What is this? It's a constant? How many people think it's a constant? Straight line. Okay. There you go. Straight line is correct. So how many points do we need to determine what a straight line is? 2. Right? Okay. So, all right. So if we have that, what 2 points would be probably best to use here? So my x bounds are 0 and 1. What would be our best points to probably use on this problem? Well, you can pick any points you want, but let's go with 0 and 1, since we're going to have to look at what the graph looks like on those points anyway. So let's go with x equals 0 and x equals 1. When x equals 0, what is my y value? 0.5, right? Or 1/2, if you like. And when x equals 1, what is my y value? 1.5. Okay, so we have this over here, and let's graph this. So my first x value is going to be 0. My second x value is going to be 1. And what is the what is the value of my function when x equals 0? 0.5, right? And so we have this point over here. And what is the value of my function when x equals 1? 1.5. All right? So that's going to be right here. Now, we have a straight line connecting. So the function is going to look like this. All right? So what I want to find is I want to find the area between the line y equals x plus 0.5 and the y-axis and the x-axis between 0 and 1. So essentially what I want to find this area right here. Okay? So I'm looking for the area beneath this curve and above the x-axis. All right? Okay. So let me just redraw it over here, and we're going to find what that area is by breaking it up into a rectangle and a triangle. So again, just to rewrite the problem, we have the definite integral from 0 to 1 of x plus 0.5 dx. And I'm just going to let this function that I'm looking at the definite integral over be x plus 0.5. And again, just the points we chose. This is my y value, this is my x value. 0.5 when x is 0, and 1.5 when x is 1. Okay? So what we had here is we had when x was 0, y was 0.5, and when x was 1, y was 1.5. So this point over here and this point over here, and someone in the class said it was a straight line. They're correct, so we just connect those 2 points by a straight line to graph it. And to find the area under here, you're going to notice what we can do is if we start at 0.5 and we just draw a line straight across till we get to 1 and stop, we notice that what we're going to do is we're going to have this region is going to be a triangle. And what is going to be the height of this triangle? 1. 1.5 minus 0.5, right, is going to have a height of 1. What is the base of this triangle? 1, right? So what is the area of this triangle? What? 1/2, right? So the area of this triangle is going to be 1/2. All right. So what is the, how about this rectangle? What's the base of this rectangle? 1. What is the height of this rectangle? 1/2, right? Okay. So what we have here is the area of the triangle. So this total area is going to be the area of the triangle plus the area of this rectangle, right? Because these two figures together give us the area below this curve, bounded above here by the x-axis. So the integral from 0 to 1 of x plus 0.5 dx, right, is going to be equal to the area of this triangle, which is 1/2, right, plus the area of this rectangle, which is also 1/2, which is going to be equal to 1. Okay? Any questions on that? Well, so the idea is that the definite integral between 2 points is going to be the area between the curve and the x-axis, right? So if we graph this function over here as a straight line, and what we're interested in is the area under this line, right? So the question is, how can we get that area? Well, one way to get the area would be to draw a straight line at 0.5, and we wind up with a triangle and a rectangle. The base of the triangle is 1. The height of the triangle is 1. So the area of a triangle is 1/2 base times height. So this has an area, I'll put a sub t for area of triangle, of 1/2. Below we have the area of this rectangle over here, which is a base of 1, a height of 1/2. And for area of rectangle, put a sub r is just base times height, which is 1 times 1/2 is 1/2. So the definite integral, which is going to be the area between the x-axis and this curve, is the area of this rectangle plus the area of this triangle. The area of the rectangle is 1/2. The area of the triangle is 1/2. The sum is equal to 1. Does that answer your question? Are there any other questions? Okay. Okay. So they essentially do it the same way, so that's fine. We're going to look at something else here, and we're going to suppose that f of x is continuous on the interval that x is less than or equal to a and x is greater than or equal to a and less than or equal to b. We're going to define the definite integral from a to b is going to be defined as the area of the positive regions, or the area where it's above the x-axis, minus the area where it's below the x-axis. Okay? So any questions on that? So basically what we're going to do, and we're going to do an example in a second, we're going to find the area of the curve where the curve is above the x-axis. And then we're going to find, and that's going to be this term over here. Then we're going to define the area of where the curve is below the x-axis. That's going to be these two areas over here. And we're going to take the area where it's above, which is a and d, and we're going to subtract the area where it's below. Okay. So to see an example of that, let's look at calculating the definite integral of -1 to 1 of the function x dx. All right? So we have the integral of -1 to 1 of x dx. And we're going to do this similar to the way we did before. So what should my function be here that I'm going to graph? We're going to approach it the same way. So I want to start off by graphing. What's going to be my function I'm going to graph here? X. Well, x is a little bit more. No, well, no, you were right. It's x, but it's I'm going to graph my function f of x, right? Just f of x equals x, or y equals x if you like. Okay, and I'm going to graph this, and I'm going to go between -1 and 1. So I'll just choose these 2 points over here. Also, what type of curve is this function? Straight line, right? So when x is -1, what is f? 0? -1, right? When x is 1, what is y? 1, right? They're equal, right? Okay, so let's graph this function. And it's 0 at the origin, okay? So when x is -1, the value of y is also -1. So that's going to be this point over here. and it's a straight line, and when x is 1, y is 1. So it's going to be a straight line connecting, that's not a very straight line. Okay, I guess it looks okay. From -1, and it's 0 in the middle. So if we look over here, we know between 0 and 1, I'm just going to put a third point here, we don't need it, but just as an illustration, when x is 0, y is 0, right? So if we're between 0 and 1, we have a triangle where the hypotenuse of this triangle is the curve that's above the x-axis. And between -1 and 0, we have another triangle over here where the hypotenuse of the triangle is just going to be the value is just going to be where the curve is below the x-axis. All right. So if we go back to what our definition was, nope, that's not what I wanted. I wanted this. Okay. If we went over here, the areas B and D are going to be like the triangle that's above the x-axis. The triangles A and C are going to be like the triangle that's below the x-axis. So we're going to find the triangle we're going to find the area of the triangle that's above the x-axis. We're going to find the area of the triangle below the x-axis, and we're going to subtract the two. Okay? So that's going to be that's how we're going to approach the problem. All right? So what is the base of this first triangle here? 1. What is the height of this triangle over here? 1. Okay? Now over here, what is going to be the base of this triangle over here? -1. Okay? Or you can and what's going to be the height of this triangle over here? -1, right? So the area of this triangle over here is going to be what? 1/2, right? It's going to be 1/2. And what is going to be the area of this triangle over here? -1/2? Half. So if we follow, I'm going to call this over here, this is going to be, A is going to be the area of this triangle, B is going to be the area of this triangle. Right? Oops. So we have A equals 1/2 and B equals 1/2. So according to our definition, what we're doing is we have the definite integral from -1 to 1 of x dx is going to be equal to the area of the curve that's where the curve is above the x-axis, and look at the area between that curve and the x-axis, which is going to be A. And the area between the curve and the x-axis where the curve is below the x-axis is going to be B. So this is going to be A minus B, which is going to be, what is A? What? 1/2, what is B? And that gives us an area of 0, right? Okay. Any questions? So the basic idea is if we're looking at the integral over some function, and say the function is positive in some areas and negative in some areas, we're going to look at the total area where the function is positive and look at the area between that curve and the x-axis. And then we're going to look at the area between that curve where the curve is negative, and we'll look at the curve in those places between there and the x-axis, and we subtract the two areas. Okay. And that's essentially what they're doing here with the same example. And all right. So now what we want to do is we're going to gain a little bit more flexibility with our tools here. Because there's a reason we define the definite integral like this, is because we can relate evaluating it to the indefinite integral. Okay? So this is very, very important, and note that f has to be continuous here. Otherwise, you can't apply it. You can have, it's not too hard to find stuff where this doesn't work, but we won't see any of it. So if you have a continuous function on the interval on the interval a to b, and f is any antiderivative of f, then the definite integral between a to b of f of x dx is equal to this antiderivative, it can be any one, minus the antiderivative evaluated at a. So just a quick question, why can we use any antiderivative we want? So any antiderivative we want. It says, let x be an antiderivative. Right? So let's look here. Suppose if we just go back to the previous section, and we want to find the indefinite integral, or 2 sections ago, of x squared dx. What would be an antiderivative of this? Yes, right? We add 1 to the exponent, we divide by that exponent. So this would be x over 3 and plus c for my constant. So someone said for an antiderivative, we could use, say, x cubed over 3 where my constant term is 0. That's one antiderivative. I'll call that f1 of x. What's another possible antiderivative? What's another antiderivative besides this one? So this is going back to section 6.1. 6.1, another antiderivative. Yeah, okay, very good. Right, so another one would be, another possible antiderivative would be x cubed divided by 3 plus 1. Of course, remember, because the derivative of a constant is 0, right? So it's not going to affect anything here. Okay, so let's look, let's take 2 points, and let's take the points right? I don't know, say 0 and 1. All right? So if anyone's having trouble reading, it says, let's take the points 0 and 1. And let's look at f1 of 1 is going to be equal to what? So if I look at my first antiderivative here, and I look at the case where f is 1, what is f of 1? 1/3, okay? And what about when f1 is 0? f1 evaluated at 0, what is that going to be? 0. Let's look at the case for my other antiderivative. Suppose I have f2 at 1. What is that going to be? And you don't have to simplify it. Well, I want you to simplify it, right? Yeah, 1 plus 1/3. And what about f2? What is that going to be? f2 evaluated at 0. What? Well, if I plug in 0 here, 0 plus 1, right? Yeah. Okay. And I'm going to write this 1/3 plus 1. Okay. Okay. Now let's subtract these two. What is 1/3 minus 0? What is 1/3 minus 0? 1/3. And how about if I subtract over here? What is 1 plus 1/3 minus 1? Well, I think I heard it. What was it? 1/3, right? Notice we got the same answer here. Now, the reason we got the same answer here is because, remember, any two antiderivatives could only differ by a constant. So when you subtract any of these two between the same 2 points, the constant term, which in this case is 1, right, is going to cancel out. If we use a different constant, it would cancel out. So we can, when we do this, we can pick any antiderivative we want, and we're generally just, we'll always take it to be the case where the constant term is 0. Why? Because it's the easiest one to work with. All right, so if we go back to our definition, f is any antiderivative. So when you use the definite integral, let's just let the constant term be 0. Any antiderivative, and the definite integral from a to b is going to be equal to an antiderivative evaluated at b minus that same antiderivative evaluated at a. Okay? So let's look at an example. And then if you have a question, we'll take a look at that. Okay, before I do this one, I'm going to do one slightly simpler. Okay, and then we'll do that one. Okay, so I'm going to look at a much simpler one, and then we'll do there. And that one is simple too. I just wanted to do one with one term, looking at the integral, a definite integral of a one-term expression. So let's look at the definite integral from 0 to 1 of x squared dx. Very, very simple problem. Very, very simple. Okay. So what's an antiderivative of this? X cubed over 3. You could use any one you want, but let's pick the simplest one. Right? So an antiderivative can be given by f of x is equal to x cubed divided by 3. All right? That is an antiderivative of x squared. It's not the only one, but it's the simplest one. So according to our theorem, this is going to be equal to f of 1 minus what? F of 0. All right? And what is f of 1 equal? 1/3. And what is f of 0 equal? 0. So this is going to be equal to 1/3 minus 0, which is equal to 1/3. Right? So all I did here is I found any antiderivative and I just evaluated it at this point minus this point. Okay? All right. So let's go back to the problem over here and let's look at this one over here. Now, something that we're going to need for this, and I don't know if I had skipped over the slide or not, is oh no, I didn't skip over the slide. I'm something in the next section. Sorry. Okay. So let's work on this problem. So what we want to do, what should be our first step for solving this problem? What should be our first step for solving this problem? Find an antiderivative for this expression over here. So let's do that. Let's find an antiderivative for this expression. So what we want to do is, our goal is to evaluate the integral from, I think it was 0 to 1. Is that right? Yeah. We want to get the integral from 0 to 1 of 3x to the 1/3 minus 1. So I'm scribbling that out. This is going to be minus 1 minus e to the 0.5x. Can everyone read that okay? I had two mistakes I crossed out. That's a minus 1, and that line was just a typo there. So it should be 3x to the 1/3 minus 1 minus e to the 0.5x. And in case my handwriting's a little off there, I'll just flash this up on the board again. I just recopied that problem. All right? Okay. Now, the idea is to find an antiderivative of that. So we're going to look for an antiderivative of this expression. So we're going to look at this is, we're going to start with 3 times x to the 1/3 minus 1 minus e to the 0.5x dx. And remember that we can simplify, when we have sums and differences, we can split the indefinite integral over sums and differences, and we can pull constants outside the integral. So this is going to be 3 times the integral of x to the 1/3 dx minus the integral of 1 dx minus the integral of e to 0.5x dx. Right? Now, if I integrate this first term, what should be the integral of my first term? So this first over here, what's an antiderivative of this one? So what do I add to my exponent? What do I always add to my exponent when I'm using the power rule? The inverse, the opposite of power. Yes? Right. So if I add 1, and I have 1 plus 1/3, that's 4/3. So this is going to be 9/4, right? Times x raised to what? 4/3. Minus, what's an antiderivative of 1? What's the antiderivative of any constant? I'm sorry, not any constant. But 1. What would be the antiderivative of 1? X. And how about for e to the 0.5x? What? Yeah, so what's 1 over 0.5? 2, right? All right, so this is going to be minus 2 e to the 0.5x plus c. All right, so I don't need the c on there because anyone will work. I can let c be 0. And I have f of x is equal to 9 over 4 x to the 4/3 minus x minus 2 times e to the 0.5x, right? That's an antiderivative. I can let c be 0. And this is going to be equal to f of 1 minus f of 0. Okay? So to find f of 1, I just plug in 1. And to find f of 0, I just plug in 0. So just f of 1 is just equal to 9/4 minus 1 minus 2 times e to the 0.5. And it's going to be minus f of 0 is just going to be equal to, if I plug in 0, I'm going to get 0 minus 0 minus 2, right? So if I subtract these two, I'm going to get approximately negative 0.047. And you can do that in your calculator or on pencil and paper. Well, you need to use your calculator because there's an e involved here. But you can work that out. If you don't come up with a right answer or something different than I did, let me know. But does everyone get the idea here? We have this expression for the definite integral. The procedure is find any antiderivative for this expression we have here. Evaluate the antiderivative at this value here at the top of the integral, which is your larger x bound, and this value over here, which is your smaller x bound. So this was our antiderivative. So we did f of 1, we calculated f at 0, and we subtracted the 2. Okay? And let me just go through this slide how they calculate that. They do the same thing. We start out with this definite integral. Using the fundamental theorem, right, because this is a continuous function, we have what we have over here is this is an antiderivative, given by f of x. This is what we found. And we're going to calculate f of 1 minus f of 0. And f of 1 is this over here. That's what I wrote on the board before. So maybe it's easier to read what they have. F of 0 is this over here. And if we subtract the two, we get approximately negative 0.047. All right? Any questions? So basically what this is allowing us to do is we have all these nice properties with the indefinite integral, and it gives us the ability to relate this to calculate the definite integral. Okay? All right, heat diffusion problem. All right, some food is placed in a freezer. After T hours, the temperature of the food is dropping at a rate of R of T degrees Fahrenheit per hour, where R of T is equal to 12 plus 4 over T plus 3 squared. And part A is compute the area under the graph of y equals R of T over the interval 0 to 2. And part B is, what does this area represent? Okay? So in order to calculate this area, we know how to calculate this area already. So, okay. So let's go over here. And I went back to the same slide. All right. Okay. So we have this over here, and we have that R of T is going to be equal to 12 plus 4 divided by T plus 3 cubed. All right? We want to calculate the definite integral over here. And this over here is a rational function, and we don't have, and since we're between 0 and 3, it's going to be continuous. A constant function is continuous, and the sum of two continuous function is again going to be continuous. So we know that we can apply the fundamental theorem here. If it's not continuous, you may not be able to apply it. Okay? But does everyone agree that this is a continuous function? Okay? Remember, rational functions are continuous on their domain, and since negative 3 is not in here, it's going to be, what were we going from 0 to, yeah, so this is going to be continuous from 0 to 2, right? Okay, so what we want to do here is part A said find the definite integral of this function between 0 and 2. So what it's asking, what the question is asking, is we want to find the definite integral from 0 to 2 of 12 plus 4 over T plus 3 cubed dt. Notice I put a dt here, not a dx, because I want to integrate with respect to time. Okay? Very important. All right. So if I do this, what does the fundamental theorem of calculus say? What did we do? How do I solve this? Find any antiderivative. So I'm going to start by looking at just the indefinite integral of 12 plus 4 divided by T plus 3 quantity cubed dt, which is going to be equal to the indefinite integral of 12 dt plus the indefinite integral of 4 times 1 over T plus 3 cubed dt. And this is going to be equal, or is that a squared? I think I copied it wrong. This is squared. Sorry. Okay. This I made a mistake writing the problem. These should be T plus 3 squared. So I have 12 plus 4 over T plus 3 squared, and I'm looking at the integral of 12 plus 4 over T plus 3 squared. Okay. So I have this over here. And what is going to be the antiderivative of 12? 12x? Well, where are the x's in this problem? 12t. Okay. And how about this one over here? It's going to be 4 times something. What's going to be the integral of 1 over t plus 3 squared? Any ideas? Okay, so this is not one of the rules we covered, but the idea sometimes is an integration a lot is we're going to guess solutions to things, and we're going to check the derivative to make sure it works. So this is going to have antiderivative -1 all over t plus 3. Okay, and we're going to go over that in a second. I'm just going to show you why that is. All right, this is a plus, this is a t, and this is a t down here. All right, and it's going to be plus a constant. So I took the indefinite integral of 12 and the indefinite integral of this, and I can let c be 0. So I'm going to have an indefinite integral. A possible antiderivative is going to be 12t minus 4 divided by t plus 3. All right? So what we can do is we can evaluate this. We can find f of 1. We can find f of 2, which is going to be equal to 12 times 2 minus 4 divided by 5, which is going to be equal to 24 minus 4/5. And our other bound was 0. Did I get that right? Was it 0? Yeah. Is going to be f of 0, which is going to be equal to 12 times 0 minus 4 divided by what? 3, which is going to be equal to 12 minus 4/3. All right? Oops, I'm sorry, my bad. It should be 0, greater, sorry. It's going to be 0 minus 4/3. All right? So if we subtract these, if you subtract these two, you're going to find that 24 minus 4/5 minus 4/3 is going to be approximately 24.5. Yeah, 24.5. Okay. So the basic idea of what we went here, and we're going to talk about the interpretation of this for part 2, is we started out with a function r of t is equal to 12 plus 4 over t plus 3 quantity squared. And we found any antiderivative, and what we wanted to do is find the integral from 0 to 2 of r of t dt. To do this, we found any antiderivative of r of t, which one can be given by f of t, is equal to 12t minus 4 over t plus 3. Now, since this is an antiderivative, the solution to this problem by the fundamental theorem of calculus, since this is a continuous function between 0 and 2, is going to be f of 2 minus f of 0. And we found that f of 2 minus f of 0 was approximately 24.53. Okay, so that's just a quick sum up of what we did here. Okay? Yeah. The what? Okay, so what happened to the square when we integrated? Okay, that's a good question. All right. So let's look at this function over here. Before we look at the an indefinite integral or an antiderivative for this term over here, does anyone have any questions on the procedure we just did? Does anyone have any on what we did? We started with this function. We wanted to find out its indefinite integral from 0 to 2. The first thing is, though, we have to make sure it's continuous. We have to make sure it's continuous from 0 to 2, right? So it's a rational function, and -3 is not in its domain, so it's going to be continuous everywhere else. So it is continuous. Any antiderivative, then using the fundamental theorem of calculus, we calculated an antiderivative, which was given by this. Then we did big F of 2 minus F of 0 and got an approximate answer of 24.5. So before we look at an antiderivative for this term over here, does anyone have any particular questions? Well, we were subtracting a negative number, so we ended up adding, right? Because if you subtract a negative number, the negatives will cancel out and you want to put a positive, and then you're not subtracting, you're actually adding.
So 24.
So it would, if I go back to the previous page, what we're going to end up doing is 24 minus 4/5 minus a -4/3. So we're going to end up adding 4/3. Does that make sense?
Yeah.
Okay. So any other questions? Okay. So before we move on to part B, let's look at one of the terms we had to find the indefinite integral was 4 over t plus 3 quantity squared dt, right? And of course I can pull the 4 out, and I'm going to write this as 1 over t plus 3 quantity squared dt, right? Now I'm going to rewrite this as 4 times the indefinite integral of t plus 3 raised to the -1 dt. All right? Now, what I'm going to do is, this kind of looks like t to the -1 dt, so I'm going to make a guess. What? Oh, I'm sorry, my bad. -2 dt, right? So what I'm going to guess is, normally what I would do, this kind of looks like, and I have to check my answer because I'm going to guess here, this kind of looks like t raised to the -2, right? So I'm going to guess, I'm going to, of course, have my 4 over here, but I'm going to add 1 to my exponent, so t plus 3, what's -2 plus 1? -1. And I'm going to divide by my exponent, so I'm going to divide by -1. So this is going to be equal to -4 times t plus 3 raised to the -1. Okay? And that's what I guessed so if I want to check to make sure this is an antiderivative, I need to take the derivative again to check to make sure this works. So I'm going to take the derivative of -4 times t plus 3 raised to the -1 dt. And of course I can pull my -4 out. So it's going to be -4 times the derivative of t plus 3 raised to the -1 dt, right? And I'm going to now to find the derivative of this, I'm going to bring the -1 in front. I'm going to subtract 1 from my exponent and multiply by the derivative of the inside. So if I bring the -1 in front, this is going to be 4 times t plus 3 raised to what power? -2. And what's the derivative of the inside? 1. So I multiply by 1, doesn't change anything. And this is going to be equal to 4 divided by t plus 3 quantity squared, right? So if I'm guessing that this is an antiderivative, so I'm starting with this term over here. I'm rewriting it like this, and I would like to guess an antiderivative. Well, it kind of looks, t plus 3 kind of looks like just t. T plus 3 to negative 2 kind of looks like t to negative 2. So I'm going to make a guess. And what I'm going to do is I'm going to add 1 to my exponent to get a negative 1. I'm going to divide by my exponent, and I'm going to get this. Now I just want to check to make sure that this is actually an antiderivative. How do I check to see if it's an antiderivative? I take the derivative and see if I get the function back. So I take my result here and see if I can go back the other way. So I start by taking the derivative. I can pull the constant out. Then what I can use is I can use the general power rule. I can bring the negative 1 in front, subtract 1 from the exponent, and look, I got exactly where I started with. Right? Okay, so that tells me that an antiderivative for this is indeed given by this. Okay? Does that kind of make sense? Right? Okay. We'll see more examples with that. Okay, so, in case I missed any one of that. All right, so part B, what does the area in A represent? I'll give you a hint. We did something, the basic idea for this we already did in the first problem that we did today. Okay? And, all right, so, any ideas? What is the area of A represent? Time? No, it doesn't represent time. Remember, we're looking at a rate of temperature change over time. So let's look at the case where R of t is a constant function. All right? So I think that's a good way to look at it. So I'm going to look at the case where R of t. Now remember okay. All right. Now remember that the definite integral is defined as basically a sum of rectangles and taking the limit as the width of the rectangles go to 0, so we fit more and more of them. So when we're thinking about part B, we can think of rectangles. All right? So I'm going to look at the case where R of t is equal to 12 degrees per hour. All right? And I'm going to look at the case over 2 hours. All right? So here's 12, and the function R of t is equal to 12, and I'm going from, say, 0 to 2 hours. Okay? So I have this rectangle over here. What is the area of this under this rectangle? What? 24. So, well, it's going to be 24 what? Degrees, right? It's going to be 24 degrees. So eventually, whatever I had at time 0, this integral is representing what the change was between what I had in degrees up to time 2, right? Because if I'm changing 12 degrees per hour for 2 hours, I have a change of 24 degrees, right? Does that kind of make sense? So notice that the integral from the definite integral from 0 to 2 of R of t dt is going to be equal to 24 degrees. Okay? And since we're defining this definite integral as just taking sums of rectangles, we can apply the same reasoning to this problem over here for part B. So what does the area in part A represent? What is that going to be? So we're changing at this rate over a time period of 2 hours. What is this R of t going to represent here? What is the definite integral going to represent? What? Yeah, it's going to be degrees, but more specifically? Well, it's going to be the change in the number, it's going to be the change in degrees for whatever our initial amount is between 0 to 2, right? That's what it was on our picture, right? Okay, so again, just to see how they approach it, first they find the definite integral. For part B, all right, same idea. And theorem 3, says just let f of x be a continuous non-negative function for x is less than or equal to b, greater than or equal to a. Let a of x be the area of this region. Then the area of a of x is just going to be defined as the definite integral between a and x. And we have 3 minutes, so I can do an example of this real quick. All right, and or at least I can start one of 2 minutes. Well, I can start it at least. Okay, so basically, if I just go back to the function, there's a few things we need here. We're going to look on a continuous function. We're going to look on a bounded interval. And we're going to let a of x be the area of the region under the graph of the function from a to x. And we're also going to require that a of x be non-negative. All right. So one candidate for this may be, I don't know, how about x squared from 1 to 2? Okay? X squared from 1 to 2 is continuous. It's polynomial. It's continuous everywhere. It's non-negative, right? Because we're squaring, so it's always positive, unless it's 0, but we're from 1 to 2. And since we're between 1 and 2, we also have a bounded interval. Okay. So what we're going to do is we're going to derive a formula in terms of x that tells us what's the area under this curve. All right. So I'm going to let my function f of x equal x squared. All right. And I'm going to look on the interval x is less than or equal to 2, greater than or equal to 1. All right. So a of x then is, that's an x, is going to be equal to the integral, say, from 1 to 2 of f of t dt. Now, I switched variables to t, I'm sorry, I wanted to put an x here. Where x is less than 2. Now, I put an x here and a t here so I don't get my variable switched up. All right? Okay, so I have this over here, and what's an antiderivative of x squared? X cubed over 3. So I'm just going to put t cubed. I'm going to put f of t is equal to t cubed over 3. And then f of x is going to be equal to x cubed over 3. And f of 1 is going to be equal to 1/3. So this is going to be, by my fundamental theorem, equal to f of x minus f of 1, which is going to be equal to x cubed over 3 minus 1/3. So a formula for the area under f of x, under the curve f of x equals x squared, where x is between 1 and 2, is going to be a of x is equal to the integral from 1 to x of f of t dt, which by the fundamental theorem is this over here. And I'll do another example next time, but we're out of time. So thank you very much, and I will see you on Wednesday. Wednesday we will be reviewing for the exam. 6.2. That's correct. And yes, if people are wondering, I'm going to cover 6.2 for the exam, primarily because there'll be some review sessions I sent out some emails. There's an online review session. And if you didn't get that, just send me an email. I'll resend it to you. And see you Wednesday. Thank you. Yeah.
I emailed you my.
Oh, hold on a second. Let me stop recording. Hold on. Okay, I guess did I forget to record? Oh, hold on. Oh, Shift F10.